This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you. PV equals nRT is called the ideal gas law equation. Simply, it says that the pressure and volume of a box depends on the number of ideal particles in the box, and the temperature of the box, and some constant of the universe. Why is this important to the history of quantum? Well, because the man who, in 1834, first stated that we can put them together, a man named Benito Paul Emile Chaperon, went on to correct the work of a young man, deceased 2 years prior, named Nicolas Carnot, which as a sort of dual effort, created the concepts of absolute temperature, entropy, and the second law of thermodynamics, all of which play a large role in quantum. Carnot set in motion the concepts of the second law by developing the notion of a reversible process and stating that no such process exists in nature. Chaperon made this idea more popular with graphical and analytical depictions of it, and by combining together the gas laws of Boyle, Charles, and Gay-Lussac. In 1847, Hermann von Helmholtz, who had been studying neurology, discovered that no energy was lost in the muscle movements, and formulated a treatise on the conservation of energy, which states that the total energy of an isolated system remains constant. Energy is conserved over time. In 1850, Rudolf Clausius put together the works of the others in a more concise and sounder form, and thus gave us the concept of entropy, which he denotes as heat lost or turned into waste. And he provides the first and second laws of thermodynamics. The first law stated that the total energy of an isolated system is constant, and the second stated that there is an irreversibility to the natural processes, that entropy increases over time. In 1859, James Clerk Maxwell creates a thought experiment called Maxwell's Demon. Who could possibly, maybe, reverse the process, and therefore violate the second law of thermodynamics? In the same year, Gustav Kirchhoff proposes his law of thermal radiation, and a year later coins the term black body, which he writes, "The supposition that bodies can be imagined which, for infinitely small thicknesses, completely absorb all incident rays, and neither reflect nor transmit any. I shall call such bodies perfectly black, or, more briefly, black bodies." At this time, these two concepts were seemingly unrelated, but that would quickly change. Kirchhoff has been working with Robert Bunsen, of the Bunsen burner, and together they burned all sorts of gases and elements, and invented the spectroscope to discover the chemical elements of the stuff that they were burning. It had been known since Newton that light creates a rainbow, and what Kirchhoff and Bunsen were doing was burning objects to make them become light-emitting. And then they took their light, similar to taking in the sunlight and turning it into a rainbow, and finding the individual colors of different chemicals. The interesting thing about these rainbows is that not all the colors show up all of the time. And this was first discovered in the sun in 1802 by William Hyde Wollaston, who noticed, through an improved version of Newton's work, that the sun did not in fact have all of the colors. Some missing patches showed up. Wollaston thought that the colors had natural boundaries, but in 1815, Joseph van Fraunhofer discovered that if you use something like Thomas Young's double-slit diffraction gradient rather than a prism, and using light interference theories, that you could quantify the wavelengths of light, thus providing the specific wavelengths of light that are missing from the solar spectra. Back to the Future of 1860, Kirchhoff and Bunsen found the same thing in reverse. As Fraunhofer was providing the characteristic absorption lines of the sun, they matched perfectly with the characteristic emission lines of different gases and elements. And they deduced that the solar atmosphere contained chemical elements which would absorb these wavelengths, thus leaving missing patches by the time the light reached Earth. In 1868, Joseph Norman Lockyer repeats the spectral analysis of the sun during a solar eclipse, and finds a prominent yellow line, about 588 nanometers in wavelength, and this line had no apparent chemical equivalent on Earth, as far as we knew. He called it helium, after the sun's Greek name Helios. 27 years later, helium would be found on Earth. Kirchhoff's black body comes from his years of burning stuff. And here is the pattern he saw. 1. You take an object. Any object will do. Notice that you can see it having certain colors under the lights of the lab or the sunlight. And notice that you cannot see the object in a pitch black room. You can see this object because it is reflecting light. 2. Burn the object. Even in the pitch black room, you can now see the object, and its color no longer depends on the wavelengths of light in the room. Rather, regardless if the lights are on or not, the object emits its own color that depends on what it is made from and how hot you burn it. 3. A black body is any object that can absorb light, but cannot reflect light, and will only emit its own radiation, its own black body radiation. This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you.